Okay, I'm going to go over the last problem we were talking about in class that included Pascal's triangle and see if we can clarify that. Suppose you roll a die 4 times, so it's a Bernoulli trial because you either get the number you're looking for or you don't, and you let x equal the number of 6s, so x is success. Find the probability model of x and the probability that you get 2 or more 6s. Well, x is the number of 6s, and they say x is approximately binomial distributed, with n being 4 because you roll the die 4 times and a chance of success again as 1/6. And a probability model is just all the possible outcomes. So there are 5 possible outcomes. You could get 0, 1, 2, 3, or 4 6s. In order to find the probability, you can look at them separately. So for the first one, you could have 0 successes and get 4 numbers that are other than a 6. And you have to think about how many ways that could happen. Well, in this case, just one. You get everything but a 6 all 4 times. So that is 4, choose 0. The next one, you could get 1 6, and that could happen 4 different ways. You could get it on the first roll, second roll, third roll, or fourth roll. And again, that's 1/6 happens once, you get the 6, and 3 times you don't. And you could, if you couldn't think out like the 4 choose 1, you could use the calculator or the formula above. The calculator, you'd go 4 choose 1 in the math setting. And you can look at all of them separately. It's pretty easy following the pattern to find the probabilities, but the number of ways it happens you may need to think about. For example, getting 2 6s, there are more than 4 ways that can happen. And a matter of fact, there are 6 ways. And instead of trying to count up all the ways, like you got a 6, not a 6, not a 6, 6, 6, not 6, 6, not 6, etc., you could look at Pascal's triangle. So we have 5 possible outcomes, 0, 1, 2, 3, or 4 6s. So we go to the 5th row of Pascal's triangle. And notice these numbers here are the number of ways in which we could get our different combinations of 6s, which I just find fascinating. There's 1, 2, 6, 1, 4, 6, 4, and 1. And I think this last one's easy to think about. How many ways can you pick 4 things if you're picking all 4 of them? Well, 1, you picked all 4 of them. Let's go to the next part. So speaking of the binomial distribution, it has an expected value of n times p and a standard deviation of the square root of npq, where n is the number of items, p is the chance of success, and then again, q is the chance of failure. And let's look at this example. Suppose that 75% of customers at a gas station choose 87 octane gas. If you observe 50 customers, so n is 50, what is the probability exactly 40, that's your x or how many you're choosing, will choose the 87 octane gas? So let's define the variables. X is the number of people who get the 87 octane gas, and X is approximately binomial distributed with 50 people or 50 trials and a 75% chance of success. So we want 40. So again, we're going to do 50, choose 40 people, and that would be really far down there on Pascal's triangle, so I'm going to let the calculator do that for me. Chance of success is 0.75, and 40 people did that. Chance of failure is 0.25. 10 people did that, and that would turn out to be about 9%. And I can use the calculator by plugging in each part or doing binom PDF. Don't forget to label N, P, and Q, or it doesn't count as work according to AP. All right, part B. What is the probability that the proportion of customers who choose 87 octane gas is 70%? Well, what they're asking for is, what's the chance that 70% of those 50 people got that type of gas? Well, 70% of 50 is 35 people. So that becomes our X, or how many we're looking for out of 50. So again, we want the probability of X equals 35. So 50 choose 35. Chance of success again of 75 happens 35 times, and 0.25 for the 15, and you should get about 0.0888 or 8.88%, and again, you could use your calculator. Now let's look at the expected value and standard deviation. We are literally just going to plug into the formula. How many customers do you expect to choose 87 octane gas? That's finding the average. So that's N times P, 50 times 0.75, or 37.5 people. The standard deviation then is the square root of NPQ. So plug that in, 50 times 0.75 times 0.25, and that's 3.06 people. So it's saying, on average, if you were to look at a group of 50 people, 37.5 of them, plus or minus 3, would get the 87 octane gas. What is the probability that the number of customers who choose 87 octane gas will be within 1 standard deviation of the mean? I do not know, well, I do, but you don't yet, the shape of the binomial distribution. So I'm just going to pretend it's kind of normal shaped and see how that works. We want 1 standard deviation above. Well, that would be at 40.56, or right here. And using the calculator, I figured out that that was about 80.836% of my curve. And then 1 standard deviation below is 0.163. Again, using my calculator, I figured out that this is about 16% of my curve. So if I want the area in between, so from here to here, then we'll just subtract the two and we get about 67.3, which is less than what we would get if it's a normal curve. So it's not quite a normal shape, and we'll look at that later. All right, so speaking of normal, the normal model to the rescue. Suppose you're a telemarketer and historically only 15% of people you call will remain on the phone for at least 1 minute. What is the probability that one of the next 5 people you call, so 1 out of 5, there's your N and X, will remain on the phone for more than 1 minute? So then X is the number of people who stay on the phone, and it's approximately binomial distributed, and we want X to be 1. So again, we could put it in our formula, or we could use PDF, and I showed you that in class. You should try it again. Don't forget to label. Should look something like this, and we would get 39.2%. Notice that PDF stands for probability density function. I like to think of the P as a point density because it's pointing to just one probability, but it really is probability density function. Now, I could ask about cumulative probabilities. And in this case, they want the probability of 1 or 0 people, the probability that nobody stays on the phone for more than 1 minute, or 1 person does. Now we're just going to add those up. So this is that probability plus the probability of 0. And so we use cumulative because cumulative adds it up. We would get about 0.835. Again, we practiced that in class. And it's just talking about here that that means it adds them all up and it goes from 0 up to some number. So if you're looking at your distribution, in this case, we had 1 person or 0 people. It went from here over. Of course, we don't have negative people, but my picture is kind of off. The calculator for binom CDF does not go to the right. It only goes to the left unless you have the TI Inspire. Let's look at this next example. If you roll a die 30 times, what is the probability that I get at least 5 6s? So again, the X is the number of sixes, and X is approximately binomial distributed with a chance of success of 0.167, or 1 out of 6. And so what we're looking for is that you've got 5 6s, 6 6s, all the way up to 30 6s. So you could just go ahead and add all of those up. So you do the first one, then you do it again for 6, 7, 8, 9, 10. I refuse. Or use the idea of at least. Okay, at least, well, if you're going from 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 30, we want at least 5. That's from here over. But remember, the calculator doesn't go to the right. So instead, since we know the whole thing is the 100%, we could do 1 minus this part, and it would give us that other area, or 1 minus binom CDF, 30 things, chance of success is 1/6, and we want 4 or less. This means probability of x being less than or equal to 4. So we're subtracting these numbers, and we end up with the answer to our question, which is 5 or more. And that should be about 0.578 or 57.8%. All right, last question before the other video. What is the probability I get at least 2 6s and at most 7 6s? So again, we're saying at least 2 and at most 7. So we want this middle amount. And remembering the calculator only goes to the left. So with this, it wouldn't be too bad. We could add up every single one from 2, 3, 4, 5, 6, and 7. Or again, we can use the idea of subtraction. So for that, we'll go from here over and then subtract from here over. And we'll be left with that middle piece that we were looking for. And I don't have that answer. You'll have to go ahead and figure that out and then watch video 2 to see what would happen if we did it 1 million times.